Okay, good afternoon to everyone. So actually, I'm finished working the assignment. I think we will discuss on Friday. Friday we'll have more times, and then the next assignment will due next Friday. Alright, the next Friday. Which Friday? So September. Did I give a wrong timing or not? No, 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 no. Wait. Which week is that? No, I mean, which week is that? Because of November is week 7, right? So what's the plan? Yeah, I mean, supposingly should be week 6. So you want week 7. Okay. I can do that, but you need to keep your project one in mind. So at the same time, you should start your project one. Okay, because the plan was you finish assignment 3 and then you have about 1 month like that to do your project one. Okay, so if we're gonna move assignment 3 forward, backwards, and then you need to start your project one earlier. Okay, no? Okay, so if we move assignment 1 to week 7, right? I think we will do tests on week 9, so that is consistent with my other class. Um, but I plan to have a revision class. So since we have moved assignment 3 to week 7, right? I think it only makes sense to do revision class on week 8. What do you think? Okay, no. Revision class. So inside that revision class, right, we will discuss, for example, week 1 to week 5 tutorial question. Okay, you go and try first. Whatever I listed up for you, go and do it. You can do extra also, and then you will bring question to the revision class. Okay, and then maybe I will provide a practice test question also, and then you can do that set also, and then we can discuss inside that revision class also. Does it make sense or not? Does it make sense? Okay. So in that case, we will find a time in week 8 to do revision class, and then week 7 assignment 3. Okay, so make sure you don't drag this deadline. I think I won't drag this deadline anymore because we already dragged by 1 week. Okay, so this is a hard deadline for week 7. Okay, so for late penalty, we have 3% if you do it without any reason. So in that case, we agree on assignment 3 week 7, and then week 8 maybe we do a revision, and then week 9 is a test. I hope to do it on the extra time, Tuesday 2 to 4, the time you gave me for replacement. So that time will replace one of the holiday at the back. We have 2 holiday to replace. Is that okay? Yeah. So that test will replace one of the class. If we really don't have enough time to cover all the syllabus in the end, maybe we need a real replacement. Okay. But if we don't need, then we will take that test as a replacement. Does it make sense? Okay. Okay. Right. So we still keep this project one here in week 10. So starting from week 7, okay, you can submit your draft for me. Okay, starting from week 7. Don't submit now because your writing is not matured yet. Tomorrow or Friday, I'll tell you what happened. Okay, how you write maths. Okay, your writing is still not mature. So you still need to learn more before you write a proper maths article or project. Okay. Yeah. You can try and uh gather material first. Okay, but your writing still need to improve. Okay. Any question so far? Is it clear for these admin stuff? Okay. Clear? Okay. Right. So this is about the admin stuff. How about lecture notes? How about previous lecture? Have you do homework or not? Have you tried out the lecture question or not? Please try, must try, find time to do it. Okay, find time to do it. Do it a bit by a bit, day by day, okay? Don't rush. Okay, if you rush, you cannot absorb the knowledge. Okay, you cannot absorb the knowledge properly. You need to do it. Okay, and right. So after every chapter, right, did you realize that I have a review exercises inside the Moodle or not? Did you see it? You know how to find it? In the week that I finish that plan to finish the chapter, I will include a review exercises. Have any one of you found it or not? Hmm? Anyone of you found it? Let me see. Can I get it for you here? Yeah. So for example, this one. In week 4, okay, you will find this chapter review question. Okay, so please try and do them. There are solution for it also. Okay, so when you do it right, don't bring a mindset that 哇，老师叫我做这题一定会考，没有这样的了。Sorry this is university, okay? University. You need to learn by understanding. Okay, use these exercises to understand the concept behind. Concept 是不会变的，题目会变，concept 是不会变。Does it make sense? Okay. So whatever I gave you, the exercises, test, question, all using same concept. Okay, concept that we learn inside this class. Okay 了，都不要想到太歪。Okay, only inside here. Okay, in this class, I want to ban a notation. I want to ban this notation. 我要禁止这个符号，这个 no. Hey, sorry. I want to ban this notation. No approximation in this class. Once you write it, it must be wrong. I never taught this in this class. Nothing like that. Did Dooley allow you to use this? Dooley allow, is it? Which part? Newton method, Yeah, that's right. Because Newton method is approximation. Only that part you use this, nothing else. Always I teach is less than equal or greater or equal to. Nothing like this. No approximation. Approximation is not precise. Either we stay on the top, either we stay at the bottom, or we stay equal. 3 cases only. Okay? Yeah, nothing like this one. If I write like this, meaning this number can jump like this, Approximate one. Okay. So no, if you have working like this, automatically wrong one, because we didn't do approximation in this class. Okay. So you make sure you have to know which part who is greater than who is less than who. Okay. Yeah. I already mentioned actually in last week class, but I think you don't understand what I say. So very important thing, you need to understand what I say. Whatever I say here is not rubbish, let me tell you. You think that I talk very slow, right? Actually, I tell a lot of important things that you think is trivial. Actually, it's not trivial. These are the things that I catch you in your assignment. Okay? Yes. So you need to listen everything what I say. If you don't understand, you have to ask. If you think that I say wrong, you should point out. Okay? Then we make sure all of us on the same page. 但是懂什么意思吗 ？On the same page， 大家读的是同一页东西 ，OK， 不是你读你的，我读我的，不是同床异梦。会吗？会华语吗？不会，喂，不可以这样华语，不会英文也不会。同床异梦sitting inside the class, think differently. Sit inside the classroom, think differently. We should think the same. We are on the same board. Yeah, same bed, same classroom in this context. Okay, so you can think differently, but make sure you match to mine or I match to yours. That's why in the start of the class, I keep asking you to prove equivalent definition, equivalent definition, equivalent definition. You can have seemingly different things, but you need to see why they point to the same thing. This is very important skill. Very, very important skill. Okay, if it's different, then you need to take counterexample. Yeah, we will speak more about this assignment on Friday. I'm still waiting some of your assignment. Please send it in soon. All right, so let's. So we have done, basically we have done Taylor series. Okay, so what's Taylor series? Maybe recall a little bit. Not the whole thing, but what did we do in Taylor series? So you're given a function f, okay? Obviously, you need what? You need infinitely differentiable function. Why? Why do we need the infinitely differentiable function? What is the Taylor series of f? Let's write like this. So Taylor series of f. What's the coefficient? Still remember or not? Taylor series is a type of what? So let's say this is about a point x equals to a. Okay. So it is a power series, first of all, right? It's a power series. Okay, let's say centered at A. But what is Cn? What's Cn? What's special about this Cn here? You need what? What is this Cn actually? How do you get Cn? You get Cn. See, I give you hint already. It has to be infinitely differentiable. Okay, so why we need it to be infinitely differentiable? What is Cn? Cn is what? Hey, don't look at me. If you don't know, go back check your note. Okay, what is Cn? What is Cn? That's someone. Is it Chung Xiang? Chung Xiang? Are you Chung Xiang? Yeah, so what is Cn? Which derivative? And then, so are you saying that Cn is equals to the derivative of f? No, so what? Okay, and then? Okay, so meaning what? Those are the n derivative of f. Okay, n, en ke, n derivative of f evaluated at the center. Divide by n factorial. Okay, so this is your Cn. Okay, does it make sense? So Taylor series of f, right, is a specific, okay, it's a specific kind of power series. Okay, specific power series. How specific is it? Is it? So with coefficient built up by the n derivative of f evaluated at the center that you expand your function. Okay, center. Divided by n factorial. Okay. Do you still remember how this n factorial comes from or not? How you get this n factorial coming up? When you try to differentiate your power series n times. If you forgot, go back and study again the proof that I showed you last time. And coming up from the differentiating the power of your power series. Okay. So today we're gonna talk about. Hey, hello. Welcome. So next, we're going to talk about Fourier series. Okay, we're going to talk about Fourier series. Hopefully, we will finish Fourier series by today because we're not going to talk about Fourier transform. Okay, so not going to talk about Fourier transform. We will just talk about Fourier series. So your first assignment question is about, I think first and second about Fourier series. But we won't talk about Fourier transform. I'll provide the notes if you want to study. So if you want to do project on Fourier series, you can just do it. Okay, I treat it as I don't taught it. So you can start from very beginning for Fourier transform. Okay, I won't teach it because it's a bit advanced. Again, if I'm gonna taught it, then I think it's not very good for you because we need to put in a lot of preliminary to tell a proper story. Otherwise, a simple calculation is kind of dumb. You can see it yourself also. And what? Yeah, it's not tested for Fourier transform. Okay, but Fourier series we will focus on Fourier series. So, what is Fourier series? So you could imagine that last time we will put powers or monomial, okay, monomial of x, power of x, as our series term. Okay, but this time we will replace this term by, for example, cosine and sine function. Okay, you will see a linear combination of sine and cosine function. And this is what Fourier series made of. So what's the context of Fourier series? Let's quickly go through here. So here, write that the power series or Taylor series is based on the idea you can write general function as an infinite series of power. Does it make sense? This line here? Sense enough. So not really general, right? We only can write for infinitely differentiable function because you need to compute the coefficient. Okay, the coefficient really depend whether you can differentiate your function or not. Right or not? Okay, so you need an infinitely differentiable function as a infinite series of power, good. But what is Fourier series here? Fourier series is we can write function as an infinite series of cosine and sine. Okay, not powers now. We put cosine and sine. So when we talk about cosine and sine, what is the image appear in front of you? You have image of cosine and sine. What's the image? Can you draw in front of you? Draw. Can you draw this? Right. Periodically. Okay, very important property is periodically. So if you look at this two function here, look at these two function. Okay, how to study these two function. So if you label this line, for example, I labeled it as minus 1, 0, 1, minus 1, 0, 1, minus 1, 0, 1. Okay, so what does it mean by add two functions together? How to add two functions together? Okay, so how we're gonna do it is we do it pointwise. Okay, we do it pointwise, meaning what? At a x, okay, at a certain x. So let's pick a nice x here. So if you look at this 2x here, if I add these 2x here, what do you get? Sorry, if you add the fx at these 2x here, what do you get? Can you see what's this fx here for the first one? Check you. What's the first fx here? Can see or not? What's the first x here? This one. You know how to read it? What's fx? So what's the value of this function at this point? You know how to read the xy axis. So what's this value here? 0. Good. Okay, how about second one? What's the value of this fx here? 0 again. So if I add point-wise at this point, what do you get? You get 0. So that's why you get a 0 point here. Okay, similarly for the other point, you can see that when they add up, they get the resultant fx. Okay, does it make sense? Maybe we pick some significant point here. How about this guy here? Why is it so low? Okay, why is it so low? Look at where it came from. Okay, you are adding two negative points. Okay. Does it make sense? Okay. Yeah. And then how about here? How about here? How about this line here? Okay, how do you get this slightly less than 0? What are you adding here? You are adding -1 with some positive number less than 1. Okay, so this is what we meant by adding point-wise. Okay, so how we add two functions? We add point-wise. Point-wise. So let's call this f, let's call this g. How we add f plus g? Okay, we simply evaluated at a point by fx plus gx. Okay, so this is what I meant just now. Does that make sense? Okay, so this is what I meant by adding two functions. Okay, yeah, try and verify for all these points. Okay, try and verify, is it true? Right. So next, the magical thing is we can make a square wave. Okay, we can make a square wave. This is a square wave. Okay, so how are we going to make this? So what we do is we start with a sine wave first. Okay, we start with a sine wave, and then we add another sine wave with different period. Okay, if you go back and plot this out, it will have a different period. Okay, so if you add them up, you will get this resultant shape here. Okay, but if you imagine I can add more and more, I can try and approximate the sine wave just now. Okay, but there's some disadvantage here. What's the disadvantage here? You can see that this part, the top part here, is usually weakly or wavy. Okay, you can't avoid it. Okay, you cannot avoid it. But how you approximate a straight line? You can add more and more weakly curve until you cannot differentiate the wave. Okay, so this is what we're going to do. Okay, so you add more and more, you can approximate the straight line here. Actually, this is how it works for your lights. Do you know it? You know how it works for your light? Who knows? Huh? Who knows? Who knows? How the light bulb works? Anyone know? Yeah. What did you know? Can you tell us? And how light bulb works? No. Yixiang, do you know? You don't know? Wei Xuan, do you know? You don't know? Anyone know? Physics 有教吗？没有。About AC and DC. What is AC and DC? Alternating current and direct current. So light bulb using alternating current or direct current? Should be alternating current. I mean, okay. So this light bulb, right? It's not just shining your. Okay, let me ask you a question. When the light bulb goes wrong, now what happens to a light bulb? It will, how to say, click, not click. It will 闪一下，闪一下这样。It will 叫什么？闪一下，闪一下。啊，喂，另外一个闪一下，你们知道吗？灯泡坏的时候不是会闪一下，闪一下吗？它其实就是闪一下，闪一下，但是它闪到很快，让你眼睛看不出它在闪。OK 了吗？It on and off at a frequency that you cannot recognize. Okay, so this is how the light bulb works. Similar here, we approximate straight line using this smaller and smaller wave. But you should notice that this square wave here, can you make a function that's straight or not? You cannot do that because your function only assign one unique number to a element in the domain. If you have a straight line here, means what? This negative pi, for example, will send to multiple point here. It's not a function. So what we can do, we can only approximate it with a very, very sloppy curve here. Very sloppy. Yeah, very sloppy curve here. Okay, this is the at most we can do. Okay, we cannot make it straight. Impossible, because this is not function. Okay, so the more we approximate, the more slanted we can go. So meaning the gradient, okay, when we approximate the straight line here, the vertical line here will get, the gradient will get more sharper, okay? More slanted, more sharp. Okay, does it make sense? Okay, so this is the idea. So we'll see how this maths work. So in this particular of chapter, right, we really only consider function that is periodic. Okay, periodic. So it repeat the patterns. Okay, for example, cosine will repeat the pattern. When you repeat the pattern for cosine, 0 to 2 pi. Okay, so you repeat the 0 to 2 pi pattern on and on. Sine is the same. So we will call this a period of 2 pi here. Okay, so if you look at this two picture here, okay, if you look at sine x, okay, after 2 pi, it repeats again. Okay, before 0, repeat also. Okay, similarly for cos. Okay. Hey, if I draw these two pictures, don't you want to ask me some question? A very naive person will ask, isn't it these two are same shape? Why are they different? Huh? Isn't they are the same shape? Okay, yeah, same, but when at point 0, they are different. But what can you observe? If you shift cos forward or backward, right, it's a same sign. Okay, same sign function. So meaning what? Cos is a shift of sine function. Sine is a shift of cos function. Okay, so you can easily deduce these equality for yourself. Okay, the formula for yourself. What's the how are they equal? Right, right. So yeah, should we talk about this? Okay, so if you look at this kind of function here, okay, look at this sign of pi x over L, you can immediately point out what is the period of this function here. Okay, so basically what you do, basically you just scale your x here. Okay, you scale your x. You scale your x. So this is about the period. Sure. Okay, let's see how this first series works. So first of all, let's take a function, okay, defined on the interval minus L to L. So you need to draw this picture for yourself. Okay, so you have a function, okay, any function from minus L to L. Minus L to L contains what? Contains 0. 0 is the middle point. Okay, so you should be symmetric about 0. Okay, so what is this function here? Maybe it's a random function like this. Okay, any function will do. And then it continues saying what f can be extended to a periodic function. How do you imagine this? If I have a function defined from minus L to L, how do I extend this periodically? Periodic, you just copy paste. No, you just copy paste this pattern here. Okay, you just copy paste, copy paste. Or you seriously just copy and paste? Okay, like this. Maybe let's move a bit to the left and paste another one. Okay. Okay, so you copy and paste here. So I mean you could write here is putting some dotted line, right? This. But obviously what? That L and minus L shouldn't have 2 points, right? So you need to decide which point you want to keep. Maybe you can throw away the top guy. Maybe throw away this guy here. Maybe throw away this. Okay, then you are fine with defining a. Okay, does it make sense? Okay, so you can repeat this pattern. So after you repeat this, we will define what is called a Fourier series of f. Okay, so what's the Fourier series of f? So this formula is pretty important for you. Okay, it's pretty important for you. So what's this formula here? Let's zoom in a little bit. So given f, okay, you can produce a Fourier series of f. Okay, it's like what we did last time on. If you have f, you can produce a Taylor series. Now you are producing Fourier series. So what's this Fourier series? Is again a series. Okay, so what series here? So here, the first term here is this constant here. Okay, we put it as a0 over 2. After you do the assignment, you will see why it's over 2 there. Okay, but for now, just leave it like that. Because it's just a constant, actually not very important, but when you try to derive something else, this 2 will come out naturally. And then the other special thing is this sum only sum from 1 to infinity. Okay, only sum from 1 to infinity because the zero term is here. And sum of what? Sum of cosine and sine with coefficient. Okay, and then this sine and cosine is not a general sine cosine. You are using n pi x over L. So what's n here? N is this indexing number here. And then L is your period. Okay, L is your period. Okay, L is your period. Not quite period, half of the period actually. Okay, half of your period. And then you have a multiple of pi here. Okay, so why are you adding sine and cosine here? Actually, they are out of phase wave. Okay, does it make sense? Out of phase wave. Just now we discussed, right? Sine is a shift of cos. Okay, so they are out of phase. So I need to tell you what is this an and bn here. Okay, and this a0. How to get them? Okay, how to get them? Like last time, how we get the coefficient of our series? We need to take our function and then differentiate it. But this time, we take our function and integrate it. Okay, we do the other way around. Okay, we integrate our function. So what is the constant term here? What you do is you integrate the whole interval that you have on the pattern that you repeat. Okay, minus L to L in this case, divided by 1 over L, and divided by half of the period. Okay, and then on fx. How about an and bn here? There's a special thing to do. You need to multiply your function with this cos and sine function. So if you look at here, okay, how you remember this? So an is a coefficient of cos. So what do? How do you find an? You multiply your function with cos first, and then you integrate. Okay, seemingly quite tedious, but this is how it goes. And for bn, you multiply with sine first, and then you integrate. Okay, for all of them, you need to divide by half of your period. Does it make sense? And follow? Later we will do exercises and examples. Okay, so for Taylor series, you differentiate, but for Fourier series, you integrate to get the coefficient. Okay. So there's nothing special about this minus L to L. We can replace it with any alpha beta. Okay, as long as you know that alpha minus beta is equals to 2L. So it's to get this L, it is half of your period. Okay, this means that to get this L, it is half of your period. So you can replace minus L to L with any interval such that you repeat the function for that interval. Does it make sense? Okay, we can replace. In principle, actually, we need to prove that, but for now, you just use it. Any questions so far? This definition is pretty important, very important for you to do your assignment. So make sure you know what is going on. Later we'll do exercise examples. But is everyone following this definition here? What you can play around with this formula for now. Does it make sense? Okay, to get the coefficient, you need to integrate. So what do you need to integrate? You need to pay attention. Okay, integrate over what interval? Actually, we don't care really. Okay, we don't care really. Just that you need to make sure that you divide by half of your period. Okay. Any question? Yes.
Can have different sets of
What do you mean? Uh-huh. Can have different sets. Are you talking about if I hit a different period, do I compute a different Fourier series? Yeah, I mean from this comment it shouldn't be. You can try and prove it. Okay, you start with the same function, the periodic function, and then maybe you pick a different period. Not to say different period, you are picking a different, yeah, right, different period. I can say different period. You can try and prove it. It shouldn't be. Otherwise, this Fourier series is not unique. It should be unique. Fourier series should be unique. Yeah. Otherwise, it's not useful. If you can have different ones. Okay. Yeah, you can try, but we won't pursue that direction. Or maybe you can do it in your project also. Okay, any questions so far? This definition 很重要. Okay, 很重要. You're gonna use this definition in your assignment. Okay. Right. So also this inequality, this equality here is also very important. Okay, so let's look carefully what these equalities do, what this formula do. So in first case, what did you see? You are integrating product of cosine and sine. Okay, so when are they zero? When these m and n are distinct non-negative integer. So let me write out in a mathematical form. So m and n is not equal. So m and n live in where? M and n live in z greater or equals to 0. Okay, so if they are distinct m n, they integrate to 0. So you can think of it, this function out of phase with each other. Cosine and cosine out of phase. Okay, when you integrate, they are 0. Okay, you can take it for granted, or you can try and prove it in your project. Okay, for assignment, you can take it for granted. So I give you hint for your assignment, you must use this in your assignment. You're gonna use these three equality. So this is the first case. How about second case? Second case was if you just take mn, any mn in z greater or equal to 0, okay, and you integrate cos and sine together. So cos and sine is already out of phase. Right, just now we have it. But if you change this mn and then integrate, you still get 0. And then for the last one, what happened when m equals to n? Okay, so these are cos square and sine square when n equals to n. The answer you get is very nice. It's actually half of your period. Okay, so that's why why the formula inside your Fourier series will only have half of your period, not 2L but L. So that's because of this equality here. Okay, because of this equality here, we will favor to discuss our case from minus L to L instead of 0 to 2L because of this calculation here. Okay, but how it exactly work out, you have to work out from your assignment question. Okay, you will see why. Okay, so the assignment question 2, I ask you to figure out why the coefficient looks like what we defined. So the most important thing is this equation here, this formula here. Because if you integrate minus L to L on cos square and sine square, you will get exactly L. Okay, but why you get exactly L, you can try and prove why. I think the last time I taught this course, someone proved this quantities. So if you like, you can go and search for it. I think it's in the 2304. Yeah, 2304 folder. I think someone proved this for their project one. Yeah, you want to know why. Okay. Do you know that you have access to previous year project or not? In the Moodle. Yeah, you can try and go and refer to what they do. If you found out that this guy do this thing, but this part don't explain well, you can actually do it again. You explain that part well. You refer to that paper. He didn't explain this well. He didn't prove this properly. So I'm gonna prove this in my project one. Also can. Okay, yeah. You can build on what people did before. This is how our mathematical paper works. Okay, we found out this part may be wrong or can further develop, and then we continue. Okay, so I'm trying to train you to be a proper paper writer here. Even though if you don't want to be a mathematician, this is a skill that you need for your life. Yes. What time is it? 1:43. Okay, so let's continue. I'm going to tell you one theorem here. So this theorem is not as nice. Maybe I don't want to talk about this theorem. I bring another more complete version of it. So let me find it. Let me find the more complete one for you. So I extract from Adams. Okay, so that's why I picked two textbook for you. So for Adam, the differences between Adam and what's the other book? Stewart. Okay, so Adam is more rigorous than Stewart. Okay, so whenever we want to go for proof, for more conceptual question, I'll go for Adams. Stewart will help you to do some calculation example then. Okay. Oh, Adam also have it, but Adam do it more rigorous. So maybe it's not too friendly to newcomers. Okay, so next is this convergence Fourier series. Okay, let me read this phrase with you. Okay, let me read with you so that you know how I read stuff. You can learn how to read a book. It's very important for you to read a book yourself, because this is how you gain knowledge. Okay, if you don't know how to read books, then it's very hard. So what did it say? So the Fourier series of a piecewise continuous periodic function f with piecewise continuous derivative converges to that function, and every point t where f is continuous. Moreover, if f is discontinuous at t equals c, then f has different but finite left and right limits c, and so on and so forth. I think if you read so long sentence, you'll get lost, right? Okay, so how to make sure you don't get lost? You need to dissect this question. Dissect this statement. How to dissect this statement? Let me tell you how to read English, okay? Today is an English class, not maths class. So how to dissect this statement? Okay, so we need to dissect this statement properly. So let's see where is the nouns, where is the adjective and so on. Where is the right? So let me see. So there's a long nouns before you get to the verb. So let's label it. How about we use highlighter? So let's use highlighter here. These holding, these holding here. Okay. This holding converge. Okay. Converge to where? Converge to something else. Converge to that function. Okay. At every point where f is continuous. Okay. So you should break this sentence into three parts first. What, and then verb, and then what. Okay. So what's the first what here? The first what here so long, so long. It is so long again. How to break this nouns? Actually, what is converging? Let me ask you a question. What is converging? Is a Fourier series converging, or is a piecewise continuous function converging, or is a periodic function converging, or is continuous derivative converging? How to read this question, function, this sentence? What is converging here? What is converging? There are few choices here. What is converging here? Which here? What is converging here? There are few choices. You must pick one. Try to pick the right one. Try first. Try.左边，谁是左边？谁在 convert 现在？哎，let me point you guys like multiple choice, right? 1, 2, 3, 4. Only 4 things. Okay, pick one. Who converge now? What is converging? 1, 2, 3, 4. 3 ah? Wow. Hey, that's it. Okay. E. How you sure is E? 其他人呢？有没有其他的猜法？我会一起 pick one。Others who is converging? 哎，玉良 pick one. What thing is converging now? 2, 3, 4. One, two, three, four. What is converging? You don't need to write what is. You don't need to read what is behind one. Just read what is before. What is converging? What is the thing that converges? So you pick 3. Okay. Any other choices? Any other choices? Okay, so the answer is Fourier series. The Fourier series is converging. Why? Let me tell you why. Okay, very important. This Fourier series of what? 谁的 Fourier series. Okay, this is Fourier series of a function. Okay, so let me draw with another color here. Of a function here. Okay, so the main point is this Fourier series of a function. But what kind of function is it? There are 3 adjectives for this function. First is piecewise continuous. Second, periodic. Third, piecewise with piecewise continuous derivative. Okay. Does it make sense? Okay. So it is a Fourier series of this f that converge. Okay. Okay. Does it make sense? Okay or not? Okay. Yeah. So converge to where? Converge to a function or to that function. Which function is this? Converges to that function at every point t where f is continuous. Okay. So it converges to some function, okay, at which this f is continuous. So that function is which function? Actually, is f, the f you started with. Okay, that function. Because there's really only one function mentioning here, f. So it says that ff will converge to f, okay, at x such that fx, f is continuous there. Okay, such that f is continuous. Okay, but what if also second line come out here? What if f is discontinuous at t equals to c? Okay, then it will have different limit from the left and right. Does it make sense? Because you are discontinuous at a point there. So meaning you come from left, come from right is a different limit. Okay. But what? So this is the very important here. So how do I put a star here? But what? But the Fourier series still converge at that discontinuity. Okay, but how to converge that? You just take the left and right limit, okay, add them up, divide by 2. Okay, maybe you seem a bit absurd, 很奇怪，为什么会这样？ Okay, so we give an example here. Okay, for example, if we start with this f here, okay, if we start with this f here, and then we make it periodic like this. Okay, we make it periodic. Sorry, I think it should be like this. Okay, we make it periodic. And we try to use Fourier series to estimate, right? So what do? We add all the sine graph, cos graph, right, to estimate. Okay, so what happened at this discontinuous point now? What happened? What happened here? You can see that you will cut through the middle of the left and right limit. It turns out. Okay, so this is what is described in this theorem here. Okay, or not? So the Fourier series will cut through the middle point of the left and right limit. Okay, does it make sense? Any question? No question. Later we'll see a real example. I will show you the real example. But this is what the theorem trying to say. Okay. Yeah. Any question so far? Any question? Any questions so far? Any question? Yeah. Okay. Yeah, about reading this theorem, it's very important for you because if you read wrong segment, right, you thought that this f is converging to f, then it's very weird for this theorem to happen. Okay, obviously f is converging to f. Okay, but actually what is converging here is the Fourier series of that f. Any question so far? Yeah, reading segment is pretty important. Pretty important. Okay, otherwise, you will understand wrong result. Because I've seen you guys using wrong segment. For example, all the tests. Okay, how do you use simple comparison test? How you use limit test? The order A and B N is very important. Who converge first and then who converge? If you change the order, then your solution will be wrong. Okay, yeah. Well, make sure you read these statement properly here. The order is very important here. Because I realize that why the MAT student, some of the MAT student here, their maths is not good because they are not sensitive to this order. Their algebra is not good. Why? Because they are not sensitive to this order. order 很重要，那个 n 啊，那个 ANBN 的排位很重要，为了方而已，不是为了小于等于大于等于，它的位置也很重要。OK。Then this is the structure. This is the structure of mathematics already. So you need to pay attention to the structure of mathematics instead of just numbering. Okay or not? Okay. Even though if you don't go to pure maths, that's fine. But you will certainly make pure maths course in this uni. So you have to learn. Okay. And otherwise, you will just suffering yourself. Does it make sense? Okay. Yeah. So pay attention to the order of these variable. It's very important. Okay. Yeah. So if there's no question, let's break until 206. We'll come back with examples. Hi.
这个地方为什么它已经收敛？
要不的，
哦，你的灯单
要证明，我们没有证，要证的话要去找那个证明。不知道应该 Adam，我忘记了，不知道 Adam 有没有证。如果他没有证，他会 refer to 另外一件事。我跟你
想就是，
如果就算从我们的刚才那个 idea 来看的话，它的收敛就是这条线吧，就这条线。但是 turns out that 它不会从下面砍过去，也不会从上面砍过去，它过去的时候肯定是通过它的中间，这是它的通。
因为
呀，
那这个东西，我就想
啊，
就它加它不一定是个常数，
为什么不一定？
因为
它这个是 constant 的，
一定是 constant。
就这两个点就去 infinity 了。我们要的是 finite。
哦，有 finite，
不然就
我没看到，
没有好讨论，应该就没有在讨论了。
这东西
也因为我们去到五线也很难去，find out 是宝的，
我没看到。
全鱼、天童、小鹏、金盛、全优子、常德奇、于峰、丁凤平、琼香、玉良、玉行、海伦。But 哦，就那边以前韩国个呢，韩国个小莹个，小莹那时候还一拼的，红姐，还有 something or something soon。你做了没？你做了？不敢教我。我就是玩一天就扣300吧，你就赶紧交，不然的话你就是扣太多。对，因为I mean 如果你真的是有什么问题不能交当天交的话，你一定要跟我说一下。
不然的话很简单的，就是迟交一定要门诊破3%，这很简单啊，你不用什么不敢交，不用这样，就是直接交。OK，所以为什么迟交？
其他可能是
其他的对，OK OK，我感觉私下安排一下时间，应该赶得来。但是如果可能你说什么身体的问题啊，还是生病啊，还是什么，我感觉现在有事情，可能我们可以通融一下了吧。我感觉如果每次拖的话都不是很好啊，对不对？anyway，就是你也没有回复啊，你有看到我在看，那你就想你没做完，那很简单嘛，敢做敢当嘛，不对？没做完就跟我讲没做完，然后你要跟我讲方案，对不对？没有什么啊，大家都是成人了，又是什么？没有做完就跟我讲没有做完，几时要做完做给我就对了。对呀，我也不是要 fail 你还是什么这样。如果你真的可能你要花比别人长一点时间，OK，那我给你通融多一点，但是绝对不能够通融到，比如说我已经发答案了，你才交啊什么的。对，但最重要是你要跟我讲，对了，对吗？啊，可以交了是不是？那赶紧交，我等着你啊。对啊，
长云，今年够快乐了，今年
怎么？怎么嘞？哎，
哎，今年有看片了吗？有看片了吗？呀，现在
2不能这样。OK， 我可以演，但是我不会一直演。演出来，有这样。
Hello, testing. All right, so let's start for the final hour here. So, right, so just now we spent time talking about the theory, the theorem, how it works. But really, we want to see the real example. Do we get this theorem that we prove? Okay, so I guess one hard part in this course, or maybe my course, was you not only need to know about concept, you also need to be practical. Okay, you need to you know how to apply on a exercises or examples, and then when you do examples, you know what is going on at the back. Okay, so these two things typically is very hard to balance. Okay, but we try to balance it. Okay, in our course. All right, so let's start with the real function here. Okay, the real function here. So when you read this function, right, this function is what kind of function? It's a piecewise continuous function. Okay, piecewise continuous function. Okay, it's a piecewise continuous function. But how is this piecewise? So when x is from -1 to 0, what do you get? You get a 0 function. But when x is going from 0 to 1, you get a function 1, constant function 1. Okay, but can I draw like this or not? So what's wrong here? What's wrong? Okay, can I have two values of f at the same point? So did I make any mistake or not? If you look it back here, what mistake I make? Not equal? Which part not equal? So actually your 0 only take from -1 to 0 strictly. Okay, so meaning you need to take away the two endpoint here. Okay. So this is your f. And then what does this fx plus 2 equals to fx means? So what this means here? Okay, so what does this mean? So we need to, how to say, we can check at every point, for example, correct or not? So I just tell you how to draw this f, but what does this f doing here? It tells you how to extend your function to all r. Okay, how to extend your function to every r here. Okay, so for example, what is the point at x equals to 1.5? Okay, so what is f 1.5 here? Can you use this formula to calculate or not? F 1.5 equals to what? How do you realize this function here? You need to relate back to what you know, right? The range that you know is from -1 to 1. So can you add something from -1 to 1 to 2 such that you get 1.5 or not? What do you add? Minus what? 0.5. Well, minus 0.5 is in which range? It's in the range of 0 function. Okay, so meaning at this point when you extend it, what do you get? You get 0 here. Okay, and then if you're gonna do it continuously, I mean, not the continuity, you continue to do it. Okay, how about check the point 2, okay, and then 2.5 like that. Okay, so what happened to 2? Okay, f2 equals to what? Equals to f of 0 plus 2. Where is 0? 0 is actually 1. Does it make sense? Okay, so if you check all the points, right, really what you see is it repeat the pattern you have. Okay, so this is what this function tells you. It repeat at a period of 2. Okay, so where's the period 2 here? Negative 1 to 1. Is it period 2 or not? 1 minus minus 1 is 2. So you repeat this pattern here. Okay, so if you graph it out, you will get this kind of picture. Okay, so this is just minus 3 to 3. So you could imagine if you extend infinitely many times, if you draw this infinitely, then you will see this 0, 1, 0, 1 pattern happening. Okay, does it make sense? Okay, so these questions may extend. Okay, so this is what we call extend. We extend a function in a period of 2. Okay, extend the function in a period of 2. Right. So you can see that they repeat at a period of 2. So after we repeat it, this is what kind of function? This is a periodic function. Okay, because they repeat the pattern. So for periodic functions, right, what do? We can find the Fourier series. Okay, so still remember or not, last hour, what's the definition of a Fourier series? What's the first term? What's the first constant here? We call it what? A0 over 2 plus 1 plus the sum of what? Sum of cos linear combination of sine and cosine function. Okay, linear combination of sine and cosine function. What? But what is inside sine and cosine here? It is what? N pi x over L. Okay, N pi x over L. And what's the coefficient in front of them? For an, we call it, for cos, we call it an. For sine, we call it bn. Okay, sum from 1 to infinity. So in this case, what is the L here? What's the L here? What's the L here? What's the interval that we pick here? Where's the pattern that we repeat? The whole interval from minus 1 to 1. Okay. Okay. So how to get the L? Still remember or not? The period is equal to the endpoint, the right endpoint minus the left endpoint. Okay, which is 2 in this case. So our L is 1. Okay, if you forgot, go back. This slide is with you, right? So we are using this formula here. Okay, let me highlight it. Okay, if your function repeat at a period of interval from alpha to beta, so how to get L? You take the right endpoint minus the left endpoint and then divided by 2. Okay. Does it make sense? Okay. So please remember this. This is the general form. Okay. The usual form is minus L to L, but we can make it general. Alpha, beta. Right. So if we further simplify this, what do we get here? We get an cos of n pi x plus bn sine n pi x. Right. So now our job is to find all these a0, an, and bn. Okay. So what's the formula for this guy? A0 is what? 1 over, okay, so should be the integral of fx, okay, dx from where to where? Depend on the interval that you repeat your pattern. In our case, where to where? If from minus 1 to 1. Okay, you need to divide this by L. So what's L in our case? Is again 1. Okay. How about an? How about an? An is integrating fx with what? With cos n pi x over L, which is 1 again. The integrating from -1 to 1 divided by 1 over L again. Okay. How about Bn? So Bn is similar to An, but you need to multiply fx with sine n pi x. Okay. Right. So we're going to compute all these numbers. Can you do it? I give you 2 minutes. See if you can do it. And try and compute these 3 numbers here. We're going to try and do this integral. Give you 3 minutes. Try and compute this integral using the definition of f. If you cannot see, actually you have this note, right? Does everyone of you have this note? Yeah, you can write on your note. So I'll try and compute this. Okay, so how it goes. So let's compute A0 first. Okay, let's compute A0 first. How do you compute this A0? Actually, half of it is already 0. Did you notice that? Okay, so the non-zero integral actually come from 0 to 1. Okay, for -1 to 0, you are integrating the 0 function. Okay, so what can you really do? Actually, you reduce this function to integrating the function 1 dx from where to where? From 0 to 1. From 0 to 1. But what is this? This is evaluating x from 0 to 1, which is just 1. Okay. Do you all get the same answer? Okay. How about second one? Second one is the same, right? The only really non-zero part is going from 0 to 1, which is 1 time cos n pi x dx. So you need to ask yourself, do you know how to integrate cos x? Okay, how do you integrate cos x? You should get sine n pi x over n pi integrating from 0 to 1. So what do you get? You get 0. Okay, you get 0. Good. Similarly for Bn, right? So for Bn, we also integrate from 0 to 1 of sine n pi x, and then what do you get? You get cos of n pi x over n pi, okay, integrating from 0 to 1. So in this case here, it's a bit non-trivial here. What's non-trivial here? You really get what? 1 minus cos n pi over n pi. Agree? Agree or not? Or should we write one more step? Maybe let's write one more step. Negative cos n pi over n pi plus 1 over n pi. But what is cos n pi? Cos n pi. So if you don't know about cos n pi, you should try n different n. Okay? When n equals to 1, what do you get? Cos pi. That's your turn. Minus 1. Cos 2 pi. Cos 2 pi is what? 1. 3 pi. Minus 1. 4 pi. 1. So you alternate between minus 1 and 1. Okay, actually depend on n, right? Okay, actually depend on n. So this is really just 1 minus 1 to the n. Okay, so if you put all these together, what do you get? So in the end, my f of x is equal to what? A0, so A0 we computed is 1 over 2 plus. So the term for cos is really 0, so what we left is the sine part. So let's do it. So we left with 1 minus 1 over n pi. Okay, so the cos part disappeared. Only have a sine part. Okay, only have a sine part. Does it seem surprising for you or not? Is this an accident why the cos part disappear? Does it seem surprising for you or not? Why the cos part disappear? Why only the sine part left? What's the difference between cosine and sine? Cosine is an even function. Sine is an odd function. It's a bit like the power we had last time. Still remember? We can express the Taylor series of cosine using even power of x and sine using odd power of x. Okay? But can you see that this function actually is odd? So if you shift your function to the bottom, you can see that it is fx equals to minus f minus x. So it's odd. Okay, actually this function is odd. Okay. That's why only sine survive inside this Fourier series. Okay. Does it make sense? Okay. So you could imagine I got sine like this. So what is this half doing? Actually, it's shifting the odd function out, shifting my sine function out. Okay, so that's why your function start with 0 to 1 instead of maybe minus 1 to 1. And then do some shifting some more, right? We scale your sine function. Okay, so the moral of the story is why only sine keep? Okay, because our function is odd. So what does this function really do? If you go back and try your GeoGebra or what or Desmos, if you go and plot out all the n power, what do you see? So by the theory we say just now, right? This function will approximate this piecewise function here. Okay, but the next question is what happened at this discontinuous point? What does the value of my Fourier series take? Okay, so just now I disclosed to you that it must converge to the half of the sum of limit from the left and right. Must be half. It cannot be, okay, let's point out this half here. So let's point it out. So where's the half? So let me write this. So this is the half. So if you're gonna approximate this function with your Fourier series, what you really get, you'll get this. Okay. Maybe you will ask a question. You could ask a question actually. When this Fourier series approximate this graph, why not? Why not when it go through this? Let me draw it more here. When it go through these this continuous point, why not it go through a bit higher then come down? Why not it go through a bit lower and then come down? Okay, turns out that it's not true. Okay, we prove that it had to go through the middle point. Okay, the limit of the addition of the middle point from the left and right. Okay, so you see, if I try to go up a bit or go down a bit, seemingly it's the other point that is near to this discontinuous point. If it goes through in the middle, then we can do a very good approximation around this discontinuous point. Does it make sense? Does it make sense? So this really restricted by the continuity of my Fourier series. Okay, if I try to be continuous, and then I don't map this middle point, you can see that it's very hard for me to go any closer to here. Only if I can go a little bit earlier to this midpoint, I can reach this point faster. Okay. If I'm gonna go a bit lower than the midpoint, then it's relatively hard for me to approximate the point that's closer to the discontinuity. Similarly here, if I go earlier, then this point is very hard to approximate already. Okay, due to my continuity. Does it make sense? Okay. Okay. Right. So let's prove it. Let's prove it. So let's not prove it, but use it. So how to use it here? So this question says that what values that this Fourier series converge at x equals 0, x equals to 1, and x equals to half. So what are these points? 0, 1, half. So let's look at it here. So where's 0, 1, half here? So 0 is at the middle, okay, 1 and half, half here. Okay. So out of these 3 points, which are the discontinuous function? Discontinuous point for my function here. Only 0 and 1. Okay. At half here, so at the half here, it is continuous. Okay. So what does the theorem tells you? Let me see. What does the theorem tells you? Okay. What does the theorem tell you? It tells you that if your function is continuous at that point, your Fourier series also converges to that point. Okay, meaning what? So your Fourier series of your function will take the value at half equals to the function value at half. So let me write down what I say. So we will have f of half equals to little f half. Okay, because this point is continuous. Okay, since f is continuous f half. Okay. Hey, imagine you need to imagine something because remember when we approximate, right, we are doing this curve stuff. Okay, doing this curve. So you need to have a lot of curve so that they really converge to this value here. Okay, can you imagine? Okay, so you really need a lot. How many of them? How many of them? What do you think? How many wavy line you need? How many you need so that you get a proper limit here to converge? How many? Not a finite n can describe. You need to describe with infinitely many n. So that's why our Fourier series go from 1 to infinity. Infinity of them. Okay. If you're gonna have finite, surely you will see this pattern. Just that when you have larger n, this wave gap smaller and smaller. Okay. Right. How about at the discontinuity point? How about at discontinuity point? What's the formula here? So let's write down the formula just now. At at the discontinuous point, what is it? It is half of the sum of the right limit and left limit. So you must converge to the middle point, okay, from the left and from the right. So if you go from right, okay, to 0, what do you get? So let's go back to this function. So if you go from right to 0, what do you get? You get 1. Go from left to 0, you get what? You get 0. Okay, so it's the half of 0 plus 1 here. Okay, left is 0, right is 1. Okay, so you get 0.5. So this is the middle point. Okay, so similarly for FF at 1, so here let's say since x equals to 0, since f is discontinuous at x equals 0 and half and 1 by the theorem. By what theorem? So that theorem, there's a name for it. By what's the name? Convergence. Okay, by convergence Fourier theorem. So we have Fourier series evaluated at a discontinuous point to be the half of the limit of the small f. Okay, going from right plus the limit going from left. Okay, so in this case, so what do we get in this case? So going from right should be 1, and then going from left is 0. Sorry. So going from left of 1 is 1, going from right of 1 is 0. So you get 0. Any question so far? So far? Okay. Okay, so if f is continuous and x equals to half, then that theorem just tells you that f half equals to little f half. So maybe let's write the last answer down to be complete. Since f is continuous, x equals to half, so by the same theorem, ff1, ff half is equals to f of, which is just 1. All right, good. So maybe you will ask a question, why are we studying Fourier series? So this D here will answer why we study Fourier series here. Okay, so it asks you to evaluate this Fourier series at x equals to half. So what happens if we evaluate this Fourier series at x equals to half? So let's write it down. So what is our Fourier series again? Our Fourier series is half plus the sum from n equals to 1 to infinity of 1 plus minus 1 to the n of n pi of sine of pi, n pi over 2. So we evaluate over 2. So from previous question, right, we actually know what this point is. What is this point? This is the continuous point, which is equals to 1. Okay, actually on the right hand side, we know it is equal to 1. But what's this big sum here? What's this big sum here? How to evaluate this big sum here? How to evaluate this big sum here? What do you think? Any idea on how to evaluate this big sum here? If you don't know how to evaluate this big sum, you should try and list down a few terms first. List down a few terms first. What's going on here? What's the first term you have? Sine pi over 2. Okay, what is sine pi over 2? 1. Sine pi over 2. Yeah, 1. Okay, good. Sine 2 pi over 2, 0. Good. Sine 3 pi over 2, minus 1. Sine 4 pi over 2, 0. So you are getting what? You are getting minus 1, 0, 1, 0, minus 1, 0, 1, 0, minus 1, 0. Okay, so you try and list all these down. So in the end, what do you get? So let's write down all the terms you get. So for the first term, you get 1 plus minus 1 to the 1, and then over pi of minus 1. Okay. What's sine pi over 1? Pi over 2. Sorry, this is 1 first. Okay, and then how about the second one? You get 1 plus minus 1 to the 2 of 2 pi of sine pi, right? So sine pi is 0. Okay, and then what's the third one? So I'll try and write all of them down. 3 pi times sine 3 pi over 2, which is minus 1. And then you keep going. Should we keep going? Let's leave it here first. So what's the pattern here? So let's move this 1/2 to the other side. Okay, move it, cancel it. So what do you get? The first one you get. Did I write something wrong? What's my Fourier series? 1 minus minus 1. Okay, so I copy it down. Okay, so for the first term you get 2 over pi, right? Second term you get 0. Third term you get 2 over 3 pi. So minus. Sorry. So it should be minus. And then you should get 0. Then can you guess the next term? Should be 2 over 5 pi. And then you keep going. Should we keep going some more? Yeah, let's go some more. If you compute 7, I think you should get negative 7 pi. And write it down if you cannot see it. Okay. So in the end, what do you get in total? Seems like doesn't look like what we want, huh? But what can you do? What can you do? Can you pull out the 2 first? Okay, can you pull out the pi also? Okay, so if you pull out the 2 and pi, what did you get? 2 and pi. You get 1 minus 1 over 3 plus 1 over 5 minus 1 over 7 plus so on. Okay, so in the end, what do you really get? You get pi over 4 equals to 1 minus 1 over 3 plus 1 over 5 minus 1 over 7 and so on. Okay. Right. Hey, remember, we've seen this before actually. When we try to do the tangent inverse thingy, compute the power series for tangent inverse. So this is the second way of getting this pi thing out. Okay. Using Fourier series. Okay. So if you think of it, how the pi appears, this pi appears from the coefficient of your Fourier series. Okay. Yeah. So if you see, we get this pi value here really simple from the what? What we call this is like a step function. Okay, so we have 0, constant function 1, and then 0, 1, 0, 1, 0, 1, 0, 1. Okay, so we just do first series of this function, and then we could get some expression for pi. Hey, did you know that recently some of the scientists or the physicists get a new expression for pi? The Indian physicists. You guys know? Rene? Yeah, some Indian physicists, they also do this kind of approximation. I don't know if it's approximation or not, but they get an expression for pi, new expression. It's quite complicated, but that one is from the experimental data. Okay, theoretical physics. Right. Okay, so let's continue. Okay, so if you want to play around with Fourier series, right, you can go and find this software here. And what can you do? You can, if you add more and more n, okay, the terms that you add into your Fourier series, you can see that the graph you see getting what? I wouldn't say getting smooth, because smooth in the mathematics we mean infinitely differentiable. You will see that the wavy part are getting less and less. Getting less meaning until it is indistinguishable. Okay, it's like the light. It keeps clipping until you cannot distinguish the frequency. You just think that it's just plain light like that. Okay. So actually this square here, don't be deceived by this square. This is not a square. It will always have a gradient, just that this gradient will approach infinity. Correct. Yeah. And because you get larger gradient. Okay. You won't get straight line, but approximate straight line very well. That's all. Okay. Okay, so again, we go through these two property. So first is about even function. What is even function? We have mentioned last time when it is f minus x equal to fx. But in this case here, this calculation will make your life easier. If you try to evaluate the integral of an even function at its period, what do you get? You just need to integrate half of it and then times 2. Okay, does it make sense? Okay, you just need to evaluate half of it and then times 2. So you don't need to do the whole integral. Okay, you just do half of it. How about odd function? Okay, odd function is a function that satisfies f minus x equal to minus fx. Odd function is even nicer. If you try to integrate this odd function over its period, what do you get? You should expect that the integral cancel out because they have different orientation, but they have the same contribution across the midpoint. Okay, so they cancel out, so you get 0. So if you try to integrate a odd function at its period, okay, then you will get 0. Okay, if it's odd on its period, then you get 0 because the negative part and the positive part will cancel. Okay. So this is the nice thing about even function and odd function. You can try and prove it. It's not hard. So I think I'll left this one as your exercise. You can try and go back and do this. It's the same story. Okay, so if you have fx equal to x squared, okay, from minus pi to pi, how to extend it? Okay, we extend it in a 2 pi. Why? Because the period is pi minus pi is 2 pi. Pi minus pi. Okay, it's 2 pi. Okay, pi minus. So you can imagine that this is your function here. Okay, so this is the periodic function. So you have a periodic function, what can you do? You can find the Fourier series. So go and get your A0, go and get your AN, go and get your BN. Maybe the integral is hard to compute, but that's how you get all the coefficients. And it's the same thing. So you just do what you learn in calculus 1. Okay, one time still got 5 minutes. So this one I just left it for you to try. So there's some nice thing about this Fourier series here. You can try and get expression for pi squared over 6 and pi squared over 2. Okay, you can write it as a series. Okay. Yeah. So this is the result of this Fourier series here. If you do appropriate substitution, okay, if you check your Fourier series as appropriate substitution. Okay, so let's continue. Still have 4 minutes. Let's see how far we can go. Okay, I think we can go. So because this is the last part we're gonna say today. So the last part about Fourier series is called the Fourier cosine series and Fourier sine series. So what's the difference between these two? So like what I said to you just now, right? Cosine function is even, but sine function is odd. So how we make sense of this into the Fourier series? So let me straight away give you an example here. So this is a choice on how we're gonna extend our function. So this is a choice of how we're gonna extend this function. So let's look at this function here. So let's draw out this function. Whenever you see piecewise function, right, you have to draw it out, okay, to see what it says. You need to draw one. Okay, for this function calculation, you need to draw. Okay, not just calculating. You need to draw it out. So how to draw? So this is defined from where to where? From 0 to 1 and 1 to 2. Okay, from 0 to 1 is what kind of function? It's a linear function. Okay, y equals to x. So y equals to x should be easy to draw, right? It's just like this. Okay, diagonal line. But what is 2 minus x? You need to start by drawing what? Minus x first. So if x is like this, minus x is what? Opposite. Okay, multiply negative to all the points. But 2 means what? You shift this function out by 2. Okay, so you shift this function out by 2. So if you go and check properly, the other part of the graph is look like this. So it's like a pyramid. It's like a pyramid. Okay, the gradient is exactly opposite. One is negative 1. So they are the same slanted but in the opposite way. 1 and negative. Okay, so the problem here is how to extend this. How to extend this function. Okay, there are a few ways to extend it. If I use the previous way, I'll tell you that fx plus 2 equals to fx. So meaning what? Meaning what you do is just like this. A bunch of a pyramid. Okay, but instead what we can do is we can extend it in an odd way. Okay, meaning we don't pick 0 to 2 as a period. We make it odd function first, only then I extend it. Okay, so this is the difference between Fourier cosine series and Fourier sine series. If you extend in an odd way, so meaning you make it odd first, you make it even first, then you extend it. This is called the Fourier cosine series. If you make your function odd first and then extend it, you will call it a Fourier sine series. Okay, so these are the two choices here you can do. Okay, obviously you can do something random lah. So maybe you do this and then you say I repeat this squeezy line and then with a pyramid. You can do it, but these two choice will be a natural choice to do, because like what I say, the nature of your series, right, is built up by even function or odd function, correct or not? Because cos is a even function, sine is a odd function. So you play around with this odd and even function. Sorry, did I say? Yeah, odd and even function. You take a linear combination of them, and then you can make nice continuous function. Okay, does it make sense? Okay, so these are two natural ways to extend it. You can extend any way you like, but these are the natural two ways you can do it. Okay, so if you extend it, then you can try and find what is the Fourier series of even extension and Fourier series of odd extension. Okay, so you can try and find these two. Right, so you try and do at home first. If you have questions, we can do it at the start of the next lecture. Okay, if not, I just provide you solution. Okay, does it make sense? I leave you back to do So in my class you have to do homework because only then you appreciate the knowledge. Otherwise you will forget one for sure. Confirm. Okay, confirm you forget if you don't do homework. Okay, you have to do at least lecture notes one. If you after you do lecture notes one, you can do tutorial one. Okay, this is how you understand these concepts. Okay, so we'll see you tomorrow. No, Friday. Friday. So if you have any question on your assignment now, please come to office hour. Okay, please come to office hour if you have any problem.